Here is a little game. The input for the game is I give you a positive integer, and then you have to do the following. Write down all the possible sum decompositions of this integer as sums of positive integers. Write them all down, all these sums. Then ignore that these are sums and just transform all the little pluses, transform them into dots so that they become multiplication. Whatever all these products are, add them, add all the things you got. And then whatever you get then as this sum, that's the output. So I've just called this a game, but really this is, I have to find a function on the positive integers really. So let me just repeat it. So input is one positive integer. Then what you do is you write down all the possible ways to write this positive integer as a sum of other positive integers. Then even though you have all these sums, instead multiply all of these numbers. Then you get all sorts of results for these multiplications, add them all up, and that's the output. So that's the function. It's a function from positive integers to positive integers. Now, this might be a little bit hard to grasp, so let me just work out a few examples. And I do this by hand. The first cases are maybe a little bit too weird to really see a pattern. So let's do one. How many ways are there to write 1 as a sum of positive integers? Well, just one. I can just write 1 itself. There's no other way. And now there's nothing to do about, you know, transforming addition into multiplication, so there's nothing I can do. So the total sum of all of this is 1. Yeah, so the input of the function is 1. Here I'll just write my computation in the middle, and here on the right I'll write the output of what my computation is. So let's do it with 2. This is already a little bit more interesting. I know 2 ways to write this as a sum of positive integers. Namely, I can just write 2 itself, or I can just write 1 plus 1. There are no other ways. Okay, so now remember the rule. I transform the pluses into multiplication. So here there is nothing to do because I have just one number. So this is a 2. And now I transform this plus into multiplication. So I compute 1 times 1. This is 1. Okay, so the output of my computations, this is 2 and 1. I just add them. I get 3. So the output of all of this is 3. So my function, if I plug in 1, outputs 1. If I plug in 2, outputs 3. Okay, now 3. How many ways are there to write this as a sum of positive integers? Well, I can just write 3, or I can write 1 plus 2, or 2 plus 1, or maybe 1 plus 1 plus 1. These are all the ways. So remember the rule. Now I have all these sums, but I ignore that. Instead, I multiply the numbers. So I get 3. 1 times 2 is 2. 2 times 1 is 2. Okay, 1 times 1 times 1 is 1. Okay. So these are the outputs of my multiplications. Now I sum them. So like 2 plus 2 is 4. 3 plus 1 is 4. So that's also 4. So I get 8. So 8 is the sum. Okay, so the output of my function is 138 so far. Let's do one more. So 4. Oh god, now it starts getting tedious. So how many ways are there to write 4 as a sum of positive integers? Okay, I can write one single 4, or I could write 1 plus 3, or 3 plus 1, or I could write 2 plus 2, or I could write 2 plus 1 plus 1, or 1 plus 2 plus 1, or maybe 1 plus 1 plus 2. Okay, and then of course I can write 1 plus 1 plus 1 plus 1. Okay, remember what we have to do is we ignore that these are sums and instead multiply these numbers. So 4 is 4. 1 times 3 is 3. 3 times 1 is 3. 2 times 2 is 4. 2 times 1 is 2, and that's the same here. So these are all 2, and I just multiply a lot of ones. Okay, so now adding starts getting tedious. So, okay, so 3 plus 3 is 6, plus a 4, I'm up to 10. And here I have another 6, then I have another 4. So if I combine these, I get a 10. So I get an extra 1, so I get 21. So 21 is the value here. So, do you see a pattern in these numbers? 1, 3, 8, 21. Let's do one more. I know it's crazy, but it's super tedious. But, you know, just for the heck of it, you know, to see the pattern. So, of course, I can write a single 5. Okay, I could write 4 plus 1 or 1 plus 4. Now let's get 3's involved. So I could write it as 3 plus 3 plus... no, that's already too much. That doesn't work. I can write it as 3 plus 2 and 2 plus 3. And as 3 plus 1 plus 1 and 1 plus 3 plus 1 and 1 plus 1 plus 3. Okay. Yeah, okay, so now maybe with more 2's, right? So I can write 2 plus 2 plus 1 and 2 plus 1 plus 2 and 1 plus 2 plus 2. I'm not sure I have enough space. Okay, now I can, of course, also replace one of the 2 by, okay, so I can write it as 1 plus 1. So that's plus 3. I already have these, plus 1 plus 2. Okay, and then, okay, so this also works. So I have 1 plus 1 plus 2 plus 1, and 1 plus 2 plus 1 plus 1, and 2 plus 1 plus 1 plus 1. Oof. Sorry, you can't even see where I'm at. And then, of course, I can write 1 plus 1 plus 1 plus 1 plus 1. Oof. Okay, but we got to do it, right? So let's multiply these numbers. So 5 is just 5. 4 times 1 is 4. 4 times 1, 1 times 4 is 4. This was an error. 3 times 2, that's 6. 2 times 3, that's also 6. 3 times, okay, so this is 3, this is also 3, this is also 3. 2 times 2 is 4. 2 times 2 is 4. 2 times 2 is 4. This is 2. This is 2. This is 2. This is 2. This is 1. Okay, now I have to add all these numbers. Oh, God. I'll go crazy, I think. Let's see. So I've, let's try to collect them in a smart way. So I've these two, 6 and 6 is 12. And here I have 3, 3, so that's 9. 3 times 4, so that's another 12. So 4 times 2, so that's 8. Here I have another 8. So how to combine them? So 12 and 8, that's 20. This 12 and 8, that's another 20. Maybe this 9 and this 1 down here, they combine to 10. So I get another extra 10. And then I have a 5 up here, which I haven't taken into consideration. So I have 10 plus 20, that's 30, 40, 55. So I have 55 here. So these are the numbers. Can you see the pattern? 1, 3, 8, 21, 55. Well, if you haven't discovered the pattern yet, let me help you out. What if I just invent another 1 here, which isn't there, but let's just invent it. Then, of course, 1 plus 1 is 2, and 2 plus 3 is 5, and 3 plus 5 is 8, and 5 plus 8, that's 13, and 8 plus 13, that's 21, and 13 plus 21, that's 34, and 34 plus 21, that's 55. What have I done here? Really, we've just been talking about these blue values here, right? These were the values which were really the output of our little game, of our little mysterious function. But the other numbers, what I've just plugged in, these are just the numbers of the Fibonacci sequence, right? This is just the sum of any 2 entries of the sequence is the next entry. 1 plus 1 is 2, 2 plus 3 is 5, and so on. So what we've just observed is that, oddly enough, it appears that this wild, crazy game that I've done here, where, we just write down sums of things and then we just multiply them, this seems to be giving, basically half of the Fibonacci sequence, right? This is just like every second entry of the Fibonacci sequence. And this is not just a funny coincidence, which is just true for the first terms. It's true in general. It's a theorem. So this little game we played here outputs precisely all the odd indexed Fibonacci numbers. And let's prove it. The proof is based on an observation what happens when you expand brackets in a product, and in these factors in the product you have big sums. So imagine maybe you have this situation. You have some sum a0 plus a1 plus a2 and so on, and you multiply this with another bracket of similar type. So b0 plus b1 plus b2 and so on. Now, how do you actually expand this? What do you get when you expand this product? Well, I mean, you get a sum where all the terms are of the shape ai times bj. So you just pick one of the summands in the left product factor and one of the summands in the right factor. You get the sum over all of these factors. Good. So this is quite interesting when you actually consider polynomials. So maybe let's consider this. So now, instead of a general sum, I'll just consider a polynomial in the variable z. So maybe at the beginning with all coefficients 1. So then maybe one of these summands is of the shape z to the a. You know, and then here are all the other summands of the polynomial, the other monomials of the other degrees. And I multiply this. And here I have some monomial z to the b. And when I expand this, of course, what I get is, again, a sum of all these pairs, you know. But among them, there will be za times z to the b. And you know, like all the other summands. So, of course, this is the same as z to the a plus b. But what could happen now is that there are maybe some other monomials in here. So maybe here there could be some z to the c. And here maybe some z to the d in this sum. And it could happen, so because these are in here, you know, it's somewhere in this big sum, you get z to the c times z to the d, which of course simplifies to z to the c plus d. But of course what could happen is that a plus b is the same as c plus d. So really what would happen is that you get this monomial twice. Okay, so this is a general observation in such products, and we ought to generalize this a little bit. So imagine now we really consider a general polynomial, then what will be the summands look like? Well, there will be something with a coefficient, so maybe ca times z to the a, and in the second factor something like c tilde. I should give the coefficients a different name. In the second factor, c tilde b times z to the b. You know, I'm just picking like two possible summands, what they could look like in this product. And when I expand this, I now know what I get will actually be the sum over all the pairs of exponents which add up to some fixed value n. So I'll get the polynomial in all the degrees. So I get this, I run through all values a, b, such that a plus b is the same value n, this value here. And I get the coefficient c a times c tilde b, all of this, and this will be the coefficient for z to the n. Okay, just maybe to elaborate a little bit, to completely make clear what's happening here. Remember, we run, when expanding this product, we just, all the summands down here mean that we pick a monomial here and we pick a monomial here, and then we get a monomial in the product. Except for, as we had just observed, whenever it happens that the sum of the exponents actually is the same value, then this really is the same monomial. So really what we get is this monomial, but with some multiplicity. Now, if instead of just having all coefficients 1 in front of these, we have some more interesting coefficients, then of course when you multiply these terms, these coefficients get multiplied. So that means when you multiply such a term with such a term, you get such a term, you know, assuming that a plus b is n. But as there might be many summands up here, which all have the property that the respective exponents a plus b sum to the same value n, you know, we might not just get one single pair ca times cb tilde, but several. And this exactly unravels this expression. So here I've expanded the resulting polynomial in n, and the coefficient will be just running through all pairs ab. You know, I could even write ab at least 0, such that a plus b equals n, and then you multiply all the respective coefficients that you get up here. And this is exactly all the contributions you get for zn in here. Good. Now this is the key observation which we need for the proof. Now my claim is that what we should look at is the following expression. We should consider the expression x plus 2x squared plus 3x cubed plus 4x to the fourth plus 5x to the fifth and so on, infinite sum, to the mth power. Well, why should we consider this? Now, I had just shown you what happens when you have such an expression and you have two factors. But of course, the same observation is true if you have more factors, for example, m factors. All that happens is that instead of running through just sums of two terms, which might add up to n, you might now just add through several. And let's actually do this. So for the general term, now let's just consider a power, because that's all we need. So Ca times z to the a something, and I take the mth power, then what I get as a generalization of this observation up here is I'm getting a polynomial. I'm running through all the possible values for n, but now I get a sum over all a1, a2, and so on, am, all of these at least 0, such that a1 plus a2 plus and so on till am add up to n. And then also all the coefficients multiply, and because I just considered a power here, they're all the same. So I get ca1 times ca2 times and so on times cam. And all of this has to be added, and I get z to the n. Okay, so this is just the generalization of the observation I made up here. But instead of just two factors, I consider m factors, a power. Yeah, and instead of having decompositions where two of these exponents add up to a possible value n, I now have to add, when I multiply these, all of these exponents to get n. Okay. Now, applying this observation to this term means the following. I'll just use this formula I've just derived here. I'll use it on this expression. Yeah, so this formula up here, use it for this expression. Now what I get is that this is a polynomial in n. Okay, and now I have to raise through all the values a1 plus a2 and so on till am. They have to equal n. And yeah, I just forgot to write that also all of these are at least 1 in this case. Well, previously here I wrote at least 0, but note that in this product the exponent 0 never occurs. The smallest exponent which occurs is 1. So I might just as well demand that all of these are at least 1, and such that the sum is n. So this is exactly the same as we had up here. Okay, good. And now what I have to write is the product of all the coefficients of these terms. But note that the coefficients in this polynomial are actually the same as the exponents, right? I have the exponent is 1, the coefficient is 1. Exponent is 2, coefficient is 2. Exponent is 3, coefficient is 3. So actually what I'm multiplying here should be the coefficients of these respective terms, but that's just the same as the exponents. So I just get a1 times a2 times a3 and so on till am. And then the sum of all of these times z to the n. Okay? Now this is really the main point, because I claim that this actually is very closely related to this function, to this little game which I've explained at the beginning. Because look at what's happening. If I just look at the coefficient for zn, for a fixed value of n, then I get this sum, and I'm racing through all decompositions of the value n in m integers, positive integers, and then what I do is I multiply them. But this is exactly what we did in our little game, right? Because I told you, okay, write the number n as a sum in all possible ways. This is exactly what's happening here, only with a little constraint that we're using a sum consisting of m terms. So write n in all the possible ways that there are as a sum, but then replace all the additions by multiplications, right? This was the second step of the game. We run through all the ways how to write a number as a sum of terms. Then we ignore that it's a sum, and instead we multiply the numbers. But this is what's happening here, right? Instead of adding the numbers, we run through all of these so that they add up to n, but then we multiply them. Okay, and then the next thing I did in this game was that after we had converted all these sums to products, we had added all these values, which is exactly what this sum does. Aha. So you see what's happening here in this sum is precisely what our little game does, with one little constraint, namely that here I'm decomposing the value n in precisely m positive integers. And in our little game, in our function, we had no such constraint, right? We were just allowing, you were allowed to write a positive integer as any sort of decomposition into positive integers. No limitation on the possible degree, on the number of summands. Good. But we can actually implement this as well, namely by just adding all of these terms for varying m, because whatever decomposition you have of a number into m into some parts, there will be a number of how many parts there are, and this number is just m. So if you allow any sort of value of m, well, it just means that what we have to do is we just have to add these terms for all possible values of m. So let me consider the following function. I define f of x to be the sum from m starting from 1 to infinity of x plus 2x squared plus 3x cubed plus 4x to the fourth and so on to the nth. And now I claim that if I actually expand this, I just noticed that I wrote a z here where it should be an x. Apologies, the variable is called x. And I claim that when I expand this in n, going from 1 to infinity, that I get precisely mn times x to the n, where mn is the output of our little game. So these are the output of our mystery function. I mean the function which we've studied at the beginning of this video, right? So I'll just call these values mn now. And I claim that this is exactly what I get when I expand all these products and sum them all. I've already gone through the entire argument, but let me just explain it a second time just to be sure. So what you get here is you have to expand all of these mth powers, which you can do using this formula up here. Then you get these coefficients in front of x to the n. But then as we have this additional sum over m, you also have to add all of these terms where now we vary through all possible values of m. But varying through all possible values of m just means that instead of considering decompositions of n into m summands, we now allow decompositions into an arbitrary number of summands. Good. So this means these mysterious numbers mn, for which we already observed that they appear to be kind of every second Fibonacci number, I have them here now. And I have a completely different way to write down this function down here, namely in this shape. Good. And now we take it from here. Because the next observation we can make is that this function actually, we can write this in a different way. This looks a lot like a geometric series or like the derivative of it. And let me make this precise. Remember the geometric series. So 1 divided by 1 minus x. That's just the sum running over all n, at least 0, of x to the n. Good. Now this is not the same thing as I'm observing here, because the coefficients aren't matching. But I could take the derivative of this, so I get 1 divided by 1 minus x squared, right? Remember, basically I have to apply the quotient rule, right? The denominator gets squared and, oh no, you can just use that this is 1 minus x to the minus 1. And then you get this derivative. There's no negative sign because you also get a minus 1 from the coefficient of x in here by the chain rule. Okay, and the derivative here, this is of course n times x to the n minus 1. This is still not quite what I want, because here the exponents and the coefficients are really the same, whereas here I have a little shift, right? Here I have, and the exponent is n minus 1 and the coefficient is n. But of course I can just fix this little issue by multiplying by x, right? If I multiply this by x, I just get the sum from 0 to infinity of n times x to the n. And this is almost the function I'm considering, right? There's a little bit of a problem because somehow the sum starts at 0. But of course, because I have a 0 here as well, this summand is actually 0. So really, the non-zero summands only start at n equals to 1. And then I really get 1 times x to the first, 2 times x to the second, 3 times x to the cubed, and so on, which is really precisely the expression as we had up here. So this term up here inside of this bracket is actually the same thing as this function down here. So let's just spell this out differently. So what have we discovered? I have now discovered that I can write, let me create some space. I've now discovered that I can write the function which encodes the values mn of our game in its coefficients. I can write this as the sum from m from 1 till infinity of x plus 2x squared plus 3x cubed and so on to the m. I can write this in a different way. This is the same thing as the sum over the functions, and it was x divided by 1 minus x squared to the m. This is the function we had. Okay, but now actually I recognize another geometric series, right? Because I'm just taking powers of this term. So I have to be a little bit careful because I start summing at 1. So let me just take one of these factors out. So I get x divided by 1 minus x squared times, and now I can start the summation at 0. Yeah, this is a standard trick, right? I mean, so I want the sum to start at 1. So what I do is I consider the same sum, but I start at 0. I multiply by one of the factors so that effectively this shifts all of these so that it was as if I would start the summation with 1. Good. So now here, this really is a geometric series. I can do all of this entire computation in formal power series, so I don't need to worry about convergence. So I get this. And then this is 1 divided by 1 minus, and now x divided by 1 minus x squared. Okay, this looks somewhat complicated, but let's simplify it. I mean, multiplying this with this will actually just get rid of this denominator. So that's cool. So what do I get? Okay, so on the numerator will be x. Then I multiply this with 1, so I get 1 minus x squared minus, and now I multiply this with this, which just cancels this denominator, so I get x. Okay, so I can simplify this. This is 1 minus 2x plus x squared minus x. And this is x divided by, so I have 1, and then I have minus 2x minus x, so I have minus 3x plus x squared. Yeah, and that's interesting. So that means that even though these numbers mn, which used to be very mysterious so far, right? I mean, these numbers came out of this complicated game of writing down all the ways to decompose a number into positive integer summands, then multiplying them and adding them. All this entire complicated procedure, this has all been packaged in these numbers mn. And now actually I've discovered that this function, which I've defined using these numbers, is actually very simple. This is actually an easy function. Good. So now we somehow need to connect this to the Fibonacci numbers, right? Because this was a little bit our observation, that it appears that these mn give the Fibonacci numbers. So how do I do this? Now the main trick is, let's just multiply this identity with this denominator here and then compare coefficients. Okay, I can do that. Okay, so I get 1 minus 3x plus x squared times the sum from 1 to infinity of mm times x to the m, and this is the same as x. Yeah, so this is just what used to be the denominator, which was on the right hand side, now it's on the left hand side. Nothing else happened. Now I expand this, so which is easy. So 1 times this is sum from 1 to infinity, so this is mm times x to the m, then minus. Okay, so now again the sum from 1 to infinity, now 3 times mm, and now x to the m plus 1, and this plus 1 comes from the extra x that I'm multiplying with. And the last term, again the sum from 1 to infinity of mm times x to the m and plus 2 because of the square I'm multiplying with. Okay, and this is the same as x still. Good, now I'm a little bit upset about all the exponents being different here, so I'll re-index the sums so that they all get the same exponents. So the first sum is actually fine. I won't be doing anything here. The second one, you see the first summand I actually get, m is 1, so the first exponent I get is 2. So let me just start this sum at 2. So I get 3m minus 1 x to the m. So see what I've been doing here is I've just replaced m by m minus 1. So this kills the plus 1 here. Here m has become m minus 1. Now I start summation at 2. It's the same sum. Okay, and I also do the same trick here. So you see the first exponent that I have here is m is 1, so the first exponent is 3. So let me just start this sum at 3. So I need to replace m by m minus 2. So m by m minus 2, x to the m is the same as x. Okay, and now I have 3 times exactly the same term. So I can collect these. So what I really get is that mm minus 3 times m lowercase m minus 1 plus capital M lowercase m minus 2 is the same thing as. Okay, and now comes the trick. So what is this? This is just the coefficient of x to the m, lowercase m, which occurs on the left-hand side of the equation. But as this is a power series, and then we have an equality, and this is a power series, well, it's polynomial. It's just a single x. But this just means it's a power series where, I mean, above exponent 1, all the coefficients are 0. But that means because the coefficients of a power series expansion are unique, that also all these values must be 0. Well, at least for m, lowercase m, at least 2, right? For lowercase m equal to 1, we would, for example, expect that these values rather are 1 because the coefficient is 1. But okay, so for m at least 2, we expect these to have the joint coefficient 0. And now you have to be a little bit more careful because even if m is at least 2, note that this means that, for example, the first summand would not actually be there because we only start summation here at 3. So let me simply assume lowercase m is at least 3. This means that under simplification, we have started the summation. So all of these summands are really there. So we get this as the coefficient of x to the m, and because there is no such, because this term doesn't occur on the right-hand side, this must be 0. So we've just obtained a very interesting identity. And we can now use this to get a recursive definition of the values mm, right? Because this means that mm is the same thing as 3 times m minus 1 minus m lowercase m minus 2, at least when m is at least 3. Good. So now this is interesting because so far when we wanted to compute the values of our game, of our little function, this was very complicated, right? You had to write the number as the sum of all of these terms, multiply them, add them, a very complicated procedure. Now we've already learned something very interesting, namely, instead, you could have just computed some very first terms, and then you can compute all the rest of the terms using this simple recursion, which is really an easy formula. So of course, this gives us a great idea how we can prove that these numbers actually agree with every second Fibonacci number. All we have to do is we have to show that if we consider the sequence of every second Fibonacci number, that they satisfy the same recursion, and of course that the starting values in the low range agree. And then that gives an inductive proof that these values agree. Good. So we need to check that if we define a sequence based on every second Fibonacci number, that it satisfies the same recursion and has the same initial values. Good. So I will now define nm as the Fibonacci number, f means the Fibonacci sequence, 2m minus 1. So let me maybe put this here. So where fm is the mth Fibonacci number. So where does this come from? Well, we had already observed initially that we get every second Fibonacci number, and actually we got the odd indexed ones, right? I had right in the beginning, when I was kind of discovering the Fibonacci sequence in the output of our little game, I had to write a little one before the first term of our sequence. So this should be the odd indexed Fibonacci numbers. which is exactly what I have here. Okay, so this is the definition of a sequence NM. And now what I dream of is that this sequence would satisfy the same recursion equation. So let's see. Let's remember this. This is our inspiration. So what I now do is, first of all, I need a little computation, namely, let me just check what this is, this right-hand side, in terms of the sequence n. So I will just I will just first compute what 3nm minus 1 minus nm minus 2 is. Yeah, so I'm just, in order to get the comparison to the sequence m, let me just compute what this is for the Fibonacci numbers. And I get that this is 3 times the Fibonacci number 2m minus 1 minus 1. Yeah, I'm just plugging in, minus the Fibonacci number 2 m minus 2 minus 1. Okay, and now I need to unravel what these are. So this is 3 times f of 2m minus 2 minus 1, so minus 3, minus f, and I get 2m minus 4 minus 1, so I get 2m minus 5. Okay, so this is the first useful identity. And now let's get started. So what is nm? Nm, by definition, was the 2m minus first Fibonacci number. Now, the key defining property of the Fibonacci sequence is, of course, that every entry is the sum of its previous two terms. So I can use the recursion of the Fibonacci sequence. So this is the same as the sum of 2m minus 2 and f 2m minus 3, right? So all I've used to go from here to here is the defining property of the Fibonacci sequence. Okay, now I'll play the same game with the first term here, because that's also an entry in the Fibonacci sequence. So I can use the same observation. So this also is the sum of the entries, the two entries before it. So this is the sum of 2m f2m minus 3 plus f2m minus 4. And then, of course, I still have this summand here. So this is f2m minus 3. Okay, so now something interesting happens because I have the term 2m minus 3 and 2m minus 3 twice. So I can simplify this. This is 2 times f 2m minus 3 plus, and this term f2m minus 4. Now, why did I do this? Well, because I'm recognizing something. We did this little auxiliary computation here of this term, which we're looking for. And then we had a 3 times f2m minus 3. And here we have a 2 times f2m minus 3. This is similar, right? We notice a similarity here, except that here this happens just 3 times, and here it just happens twice. One can barely see this. So here, now it's clear. Okay, so let's just add a kind of additional summand down here so that we also get 3 times f2m minus 3, and then I have to subtract it again so that it's correct. So I'll write 3 times f2m minus 3, and now I subtract 1 copy of these. Yeah, so now I've balanced out that I'm actually using too much here. And then, of course, I still have this term f2m minus 4 here. Okay, good. Now, let me again use the defining property of the Fibonacci sequence. So this is, I won't use it here. I will use it on this term. So minus, so what is this? Again, it's the sum of the previous two terms. So this is the same as f2m minus 4 plus f2m minus 5. Okay, and then here I have 2 plus f2m minus 4. Okay, let's simplify this. So this actually is 3 f2m minus 3 minus, oh, okay, wait. So here I have f2m minus 4 with a minus, and here I have the same thing with a plus. So these actually cancel. So I only get minus f2m minus 5. Remember this? Actually, this is exactly the same thing as we had up here, right? This is also minus 2m minus 5. Good, so we've actually discovered this term up here, right? We just found this precise term. Yeah, this is exactly what I've written down here. Good, and now we can use this equation, right? Because this was the same as this term. So this is the same as 3nm minus 1 minus nm minus 2. Good, and this was a computation for nm. So all in all, combining this, we have just shown that nm is the same as 3 times nm minus 1 minus nm minus 2. This is what we've shown. But now let's just compare this to the formula we wanted to compare it to. This was this formula, which we had for m. And you see, of course, these are the same, right? And this is the proof. We've just proven that both the sequence m, which was defined in terms of our function of our game, and the sequence n, which was defined in terms of every second Fibonacci number, they satisfy the same recursion. Okay, and now to really get a proof, you also have to compare the initial values, because this is only valid starting from 3. I will not do this. Oh, wait. Actually, we have done this because, I mean, right at the beginning of the video, we went through quite some cases for m, and we already know way more than the first 3 values. I think maybe the way more, well, maybe the first fifth or something. So we do know the initial values of these, and we had already compared them to the odd indexed values of a Fibonacci sequence. So we actually have compared the initial values, and so we have a complete proof.